Okay, so for this relativity problem, we're going to take advantage of the time dilation equation, which says that the time that passes in the rest frame is equal to gamma multiplied by the time that passes in the moving frame. That's another expression of moving clocks run slow. Now, this means gamma is equal to the rest time divided by the moving time. So that would be 3.1 seconds measured in the rest frame divided by 0.77 seconds measured in the moving frame, which is 4.026. Now I'm going to set that equal to our expression for gamma, and I'm going to try to extract the velocity from this. Okay, so if I square both sides, I get 16.2 is 1 over 1 minus v squared over c squared. And then if I cross multiply, I get 16 minus, start over. I get 16.2 minus 16.2 v squared over c squared is equal to 1. And that gives me 16.2 v squared over c squared is equal to 15.2. Right? If I move this over to each side and I cancel out and I change out the minus signs and so forth. Well, so let's see. That gives me. I guess I could also write this as v squared over c squared is equal to 15.2 over 16.2, which says that v is the square root of 15.2 over 16.2 times c, which is 0.97 c. Alright, so there's our speed, expressed as a percentage of the speed of light. Just a bunch of algebra. Okay, now part B, how far do we observe the particle to travel in Earth's rest frame? Well, to find that, we're going to use distance equals velocity times time, right? And we have to make sure that the distance and the time are measured in the same frame. So that's going to be 0.97 times the speed of light for the velocity, and the time in the rest frame is 3.1 seconds. So that's 9.0 times 10 to the 8th meters. So it's going to move quite a distance. For part C, how far does the particle travel in the particle's frame? That's going to be less. The distance in the moving frame is going to be the velocity times the time in the moving frame. So that's 0.97 times the speed of light times 0.77 seconds, which is just 2.2 times 10 to the 8th meters.